Imagine standing at the absolute end of everything. Not just the end of Earth or our solar system or even our galaxy, the end of time itself. In the year 10 to 100, a number so vast it dwarfs the current age of the universe by a factor we cannot comprehend, the last remnants of matter will flicker and fade. The final black holes will evaporate into nothingness. The universe will become a cold, dark void, stretching infinitely in all directions, populated only by scattered photons drifting through an expansion that never ends. This isn't science fiction. This is thermodynamics. Every watch you've ever worn, every calendar hanging on your wall, every sunrise you've witnessed, they're all ticking toward this inevitable conclusion. The heat death of the universe isn't a possibility. It's a promise written into the fundamental laws of physics. But here's what keeps cosmologists awake at night. Recent observations suggest the universe isn't just dying. It's dying faster than we thought. And the mechanism driving this cosmic extinction reveals something deeply unsettling about the nature of reality itself. What if everything we know about energy, time, and existence is wrong? Today, we journey through evidence that challenges everything we understand about the ultimate fate of the cosmos. We'll follow the trail of entropy from the birth of the universe to its last gasping breath. We'll examine what happens when stars stop burning, when galaxies drift beyond the reach of light, and when even atomic nuclei begin to decay. The arrow of time, 2 minutes to 8 minutes. In 1850, a German physicist named Rudolf Clausius made a discovery that would fundamentally alter humanity's understanding of existence. He was studying steam engines, practical industrial machines, when he stumbled upon a law so absolute, so unbreakable, that it governs every process in the universe, from the smallest quantum interaction to the largest cosmic structure. He called it entropy. The second law of thermodynamics states that in any closed system, disorder always increases. Always. Heat flows from hot to cold, never the reverse. A broken cup never spontaneously reassembles. Perfume dispersed in a room never gathers itself back into the bottle. This seems simple, almost trivial, but the implications are staggering. Entropy is the reason you age. It's why buildings crumble. It's why stars burn out. And most crucially, it's why time only moves forward. Think about every video you've ever watched in reverse. Water leaping from the ground back into a glass. Shattered pottery reassembling itself. Smoke condensing back into a candle flame. Your mind immediately recognizes these as wrong, impossible. Why? Because they violate entropy. They represent a universe running backward. The arrow of time points in only one direction, toward maximum entropy, toward heat death. But here's the disturbing part that Clausius realized. If entropy always increases and our universe is a closed system, then eventually, inevitably, it must reach a state of maximum entropy, a state where no energy differences exist, where no work can be performed, where nothing can happen.
A state of perfect, eternal, absolute stillness. The cosmic implications. For decades, scientists debated whether the universe truly qualified as a closed system. Perhaps energy could enter from outside. Perhaps some mechanism could reverse entropy's relentless march. Then, in 1998, everything changed. Two independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, were studying distant supernovae to measure the universe's expansion rate. They expected to find that gravity was slowly decelerating the expansion, perhaps even enough to eventually reverse it into a big crunch. What they found instead earned them the Nobel Prize and fundamentally altered our cosmic destiny. The universe wasn't slowing down, it was speeding up. The expansion of space itself was accelerating, driven by a mysterious force they called dark energy. This energy comprises roughly 68% of the universe's total mass energy content. Yet, we have no idea what it is. It doesn't interact with matter or light. It exists as a property of space itself. The more space exists, the more dark energy exists. And it's tearing the cosmos apart. The measurement was precise. The universe's expansion is accelerating at a rate of approximately 73 kilometers per second per megaparsec. This means that for every 3.26 light-years of distance, space expands by 73 kilometers every second. And that rate itself is increasing. The implications for entropy became immediately horrifyingly clear. An accelerating expansion ensures the universe will never contract. It will expand forever, growing colder and more dilute with each passing eon. Galaxies will drift apart. Stars will exhaust their fuel. Black holes will evaporate. And eventually, after an incomprehensible span of time, the universe will reach a state of maximum entropy. Heat death isn't just possible, it's inevitable. But the evidence forces us to confront an uncomfortable possibility. What if the journey to heat death reveals truths about reality that challenge our deepest assumptions about time, causality, and existence itself?
Accumulating evidence, 1500 to 3500 minutes. Part A, observable signatures, 1500 to 2500 minutes. The stellar extinction, 1500 to 1800 minutes. Let's begin with something we can observe directly, the death of stars. Our sun has been burning for 4.6 billion years. It converts 600 million tons of hydrogen into helium every second through nuclear fusion, releasing the energy that sustains all life on Earth. But this process cannot continue forever. In approximately 5 billion years, the sun will exhaust its hydrogen fuel. Its core will contract and heat, eventually reaching temperatures high enough to fuse helium into carbon. The outer layers will expand dramatically, transforming our sun into a red giant that will likely engulf Mercury, Venus, and possibly Earth itself. After another billion years, the sun will shed these outer layers in a spectacular planetary nebula, leaving behind a white dwarf, a stellar corpse roughly the size of Earth, but with half the sun's mass. This white dwarf will shine not from fusion, but from residual heat, gradually cooling over trillions of years until it becomes a black dwarf, a cold, dark sphere of degenerate matter drifting through space. This isn't speculation. We've observed thousands of white dwarfs throughout our galaxy, each representing a star's final act. But here's what makes this process so significant for cosmic entropy. Stars are the universe's engines of organization. They forge heavy elements from light ones. They emit light that pushes back against the expansion. They create pockets of order in a cosmos trending toward disorder. And they're going extinct. The galaxy isolation epoch, 1800 to 2100 minutes. Currently, we can observe approximately 200 billion galaxies in the visible universe. But visible is the crucial word here. As space expands, distant galaxies recede from us at ever-increasing speeds. Once a galaxy recedes faster than the speed of light,
not through space, but because space itself is expanding, its light can never reach us. The galaxy crosses the cosmic event horizon and disappears from our observable universe forever. The Hubble Space Telescope and the James Webb Space Telescope have documented this process with stunning precision. Galaxies at redshifts greater than z equals 1.5 are already receding at significant fractions of light speed. The most distant galaxy we've detected, HD 1, lies approximately 13.5 billion light-years away and is receding at 95% of light speed. In approximately 150 billion years, a timescale that seems vast but is merely a fraction of the universe's ultimate lifespan, galaxies beyond our local group will have receded beyond the cosmic horizon. An observer in that distant future would see only the Milky Way and the Andromeda Galaxy, merged into one massive elliptical galaxy called Milkomeda, surrounded by absolute darkness. The universe will have emptied itself before their eyes. But this represents just one piece of a much larger puzzle embedded in the architecture of space-time itself. The stellar formation halt, 2100 to 2500 minutes. Stars form from clouds of hydrogen and helium that collapse under their own gravity. But this process requires specific conditions: sufficient density, the right temperature, and, crucially, available fuel. Observations from radio telescopes surveying molecular clouds throughout the Milky Way reveal a troubling trend. The rate of star formation is declining. Our galaxy currently produces approximately 1 to 2 solar masses worth of new stars per year. 5 billion years ago, that rate was 10 times higher. Why? Because the universe is running out of raw materials. Every time a star forms, it locks hydrogen away in its core. Every time a massive star goes supernova, it blasts heavy elements into space, but consumes far more hydrogen than it returns. The universe's hydrogen reservoir is finite, and we're steadily depleting it. Based on current formation rates and available fuel, astronomers calculate that the last star in the universe will ignite in approximately 100 trillion years, a timescale 7,000 times longer than the current age of the universe. After that, no new stars will ever form. The cosmos will enter what researchers call the degenerate era, when the only light comes from the slowly cooling remnants of dead stars, white dwarfs, neutron stars, and brown dwarfs that never quite achieved fusion. Professor Fred Adams of the University of Michigan, who extensively studied stellar evolution timelines, describes this period as the universe's long twilight, a dimming that stretches across timescales that dwarf human comprehension. But the evidence extends beyond stellar death into the realm of matter itself. Part B, deeper implications, 2500 to 3500 minutes. Black hole evaporation, 2500 to 2800 minutes. In 1974, Stephen Hawking made a discovery that shocked the physics community. Black holes aren't truly black. They emit radiation. Quantum mechanics predicts that particle-antiparticle pairs constantly pop into existence near a black hole's event horizon. Normally, these pairs annihilate instantly. But if they form right at the horizon's edge, one particle might fall into the black hole while the other escapes. To an outside observer, the black hole appears to emit radiation. This process is extraordinarily slow. A black hole with the mass of our Sun would take 10 to the 67 years, a number with 67 zeros after it, to evaporate completely. Supermassive black holes like the one at our galaxy's center, weighing billions of solar masses, would require 10 to the 100 years or more. But slow doesn't mean never. Eventually, every black hole in the universe will evaporate into photons and subatomic particles. These objects, The most massive, most gravitationally powerful structures in existence will vanish, contributing their mass energy to the universe's ever-increasing entropy. The evaporation process accelerates as the black hole shrinks. In its final moments, a black hole will explode in a burst of Hawking radiation equivalent to millions of nuclear bombs. Then, silence. Even the universe's ultimate repositories of gravitational order will surrender to entropy's demands.
Proton decay. But here's where it gets truly strange. According to most grand unified theories in physics, even protons, the stable particles that form atomic nuclei, eventually decay. The predicted half-life is approximately 10 to the 34 years, meaning that in that time span, half of all protons in existence would have decayed into lighter particles like positrons and pions. Experiments like the Super Kamiokande detector in Japan have searched for proton decay by monitoring enormous tanks of ultra-pure water, waiting for just one proton to spontaneously disintegrate. So far, none have. But the timescales involved are so vast that we wouldn't expect to observe any decay events in a human lifetime, or even in the lifetime of human civilization. If proton decay occurs, the implications are staggering. In 10 to the 40 years, every atom in the universe will have disintegrated. Planets, asteroids, dust grains, everything made of ordinary matter will dissolve into a diffuse soup of subatomic particles and radiation. The very substance of reality will evaporate. The final energy state. The most remarkable discovery involves what happens after even protons decay. Physicists have calculated that the universe will eventually reach a state called maximal entropy configuration. In this state, all matter has been converted to energy. All energy has been distributed uniformly across space. The temperature everywhere approaches absolute zero, not because heat has been destroyed, but because it has been distributed so thinly that no usable energy differences remain. No temperature gradients mean no energy flow. No energy flow means no work can be performed. No work means no change. No change means time, in any meaningful sense, stops. The universe becomes a vast expanse of scattered photons drifting through ever-expanding space, their wavelengths stretched by cosmic expansion until they carry virtually no energy. The average temperature hovers just a fraction of a degree above absolute zero. Recent observations from the Planck satellite have measured the universe's current average temperature at 2.73 Kelvin. That's already incredibly cold, but calculations show that in the heat death scenario, temperatures will ultimately approach 10 to the minus 30 Kelvin, a number so close to absolute zero that the distinction becomes physically meaningless. At this point, entropy has reached its maximum. Nothing can happen because there's no energy available to make anything happen. The universe has died not with a bang, but with an endless, silent whimper. The evidence extends beyond physics into the realm of information theory and quantum mechanics, revealing something even stranger about the nature of the final state. Transition. Act 3, the big picture. Part A, theoretical framework. Entropy and information. Modern physics has revealed a profound connection between entropy and information. In the 1960s, physicist Rolf Landauer proved that information is physical. Erasing information generates heat, increasing entropy. This seemingly abstract idea has concrete consequences for the universe's fate. Every physical system contains information: the position of atoms, the spin of electrons, the distribution of energy. As the universe evolves toward maximum entropy, this information is gradually destroyed, not hidden or preserved, actually destroyed. Consider a book.
it contains information encoded in the arrangement of ink molecules on paper. Burn the book, and the information seems lost. But physicist John Wheeler argued that, in principle, you could reconstruct the book by tracking every smoke particle, every photon of heat, every atom scattered in the combustion. The information is scrambled, not destroyed. But heat death is different. When the universe reaches maximum entropy, information cannot be retrieved because there's nothing to distinguish one region of space from another. Everything is uniformly distributed. The information about how stars were arranged, how galaxies clustered, how matter organized itself, all of it erased by entropy's relentless march. Leonard Susskind of Stanford University describes this as the ultimate information holocaust. Once heat death occurs, the universe's entire history becomes inaccessible, even in principle. This forces us to reconsider fundamental assumptions about the permanence of information and the nature of physical law itself. Competing interpretations. Not all physicists agree on the inevitability or finality of heat death. Several alternative scenarios have been proposed. The Big Rip. If dark energy strength increases over time, a possibility consistent with some observations, the acceleration could become so extreme that it tears apart galaxies, stars, planets, molecules, atoms, and even subatomic particles. The universe would literally be ripped apart in approximately 22 billion years. Calculations by Robert Caldwell suggest this scenario cannot be ruled out based on current data. Vacuum decay. Quantum field theory predicts that our universe might exist in a false vacuum, a metastable state that appears stable but isn't truly at the lowest energy level. If this is true, a tiny quantum fluctuation could trigger a bubble of true vacuum that expands